Welcome to the Logic 1 course. During this course we learn the very basics of logic. The course is divided into short lectures, sets of solved problems, and sets of problems for you to solve. Emphasis in this course is in learning some basic methods that can be used to solve problems involving concepts from logic. In today's lecture, we start the first of the two main topics of this course, the topic of propositional logic. Propositional logic is a method for understanding how we use the words and, or, not, etc. in everyday language and in science. During the course, we find systematic ways to check whether an argument involving these so-called connectives is correct or not. It is important to understand that most sentences in everyday language and in science have, in addition to the above-mentioned connectives, also other logical concepts. So when we only focus on and, or, not, etc., we make a huge simplification. However, this is a useful simplification. Later, during this course, we learn how to deal with more complex expressions. In some sense, logic is one of the fundamental building blocks of science, something that mankind realized centuries ago. Nowadays, it is also true that a lot of the electronic environment we live in, such as internet, computers, mobile phones, etc., are based on logic. In a sense, logic is a common language between humans and computers, and perhaps the only common language. Therefore, it is not surprising that logic has an important position not only in mathematics and philosophy, but also in computer science. Now we shall introduce the concept of a propositional formula. Intuitively, a propositional formula is an assertion, a sentence which expresses how things are, something which can be thought to be true or false. Here are some examples. X less than 10. X less than 10 implies x squared less than 100. Left parenthesis x equals 10 and y equals 12 right parenthesis and left parenthesis z equals 4 or z equals 5 right parenthesis. It is raining or snowing. The first three examples are from the arithmetic of natural numbers, and they are true or false depending on what x, y, and z are. The last example is from natural language, and it is true or false depending on, well, the weather. Not all sequences of words are propositional formulas. Take, for example, x plus 10, sine x. I promise that he comes. Stop that. The first two are mathematical formulas. They have some value, depending on the value of x, but they do not have a meaning as something that is true or false. The third one, I promise that he comes, is a kind of speech act, but it is not a true or false sentence, although I promised that he comes would be. The last example, stop that, is also a speech act, not a true or false sentence. In this course, it is not very important to have a sharp ear to what is a propositional formula and what is not. In fact, we will give now a mathematical definition of propositional formulas, and then everything is clear. We now give a mathematical definition of propositional formulas. The advantage of a mathematical definition is that we can then use mathematical methods for the study of such formulas. The phrase mathematical definition means here more or less the same as a precise definition. When some language is defined in this kind of precise way, it becomes what is called a formal language. Nobody speaks a formal language except perhaps a computer when it is quote thinking unquote. A formal language is a model of a real language. The simplest propositional formulas are the mere proposition symbols P0, P1, P2, and so forth. We call these simplest formulas atomic formulas. When we look at a mathematical sentence, like if x less than 10, then x greater than 5, and if not x less than 10, then x greater than 15, the atomic formulas are x less than 10, x greater than 5, and x greater than 15. We could replace them by proposition symbols P0, P1, and P2. It doesn't matter which Pn we use as long as we are systematic. When we replace, say, x less than 10 by P0, we lose some information because obviously x less than 10 is more informative than P0. This loss of information is essential in propositional logic. By giving up some information, we achieve freedom, which is useful, as we see later. So don't worry when you see information disappear when we pass from natural or mathematical language to the formal language of propositional logic. In the sentence, if it rains, then it blows, and if it blows, then it gets cloudy. The atomic formulas are it rains, it blows, and it gets cloudy. They are atomic because we cannot break them into smaller pieces by means provided by propositional logic. Again, we can replace them by P0, P1, and P2, and from the point of view of propositional logic, the meaning of the sentence would not change. Perhaps some resistance builds up in your mind. How can you take such nice sentences like it rains, it blows, it gets cloudy, and replace them with those cold technical symbols P0, P1, P2, and still maintain that this tells us something about the original sentence? Welcome to the world of propositional logic. Even after the bold replacement, we can see the logical structure of the original sentence. This is the point of logic. But let us carry on. The propositional operations are negation, name for not; conjunction, name and symbol for and; disjunction, special symbol and name for or; implication, special arrow symbol for the operation if, then; and equivalence, a double arrow, and the name for the propositional operation if and only if. Parentheses are used for clarity. These are the so-called connectives. They are used to form more complex sentences from atomic ones. Natural language abounds these little words, and we have a pretty good understanding about their meaning. However, we shall in a moment define their meaning mathematically and thereby arrive at exact methods to investigate complex propositional formulas. There are also other connectives like but, unless, and so on, but we focus on the above most important ones. There are also operations that look like connectives but are not, like possibly, until, and so on. We shall see later why these cannot be treated the same way as the above connectives. In the example, if x less than 10, then x greater than 5, and if not x less than 10, then x greater than 15, we can see two occurrences of implication. One of negation and one of conjunction. In the example, if it rains, then it blows, and if it blows, then it gets cloudy, we can see one occurrence of conjunction and two occurrences of implication. We are now ready to give an exact definition of propositional formulas. The propositional formulas are of the form Pn for some n, not A, which can also be read negation A and B, which we can also read A conjunction B, A or B, which we can also read A disjunction B, A implication B, which we can also read A implies B, or also if A then B, and finally A equivalence B, which we can also read A if and only if B, where A and B are again propositional formulas. Note that we use parentheses in each case except for negation. This is an inductive definition in the sense that we build propositional formulas by starting from P0, P1 and so forth, and then use successively negation, conjunction, disjunction, implication and equivalence. Whenever we have obtained in this way some formulas A and B, we can form a new formula by applying negation to one of them or applying conjunction, disjunction, implication or equivalence to the two. And there are no other propositional formulas. Each one has to come up like this. In a moment we look at examples of propositional formulas, but let us first look at the use of parentheses in propositional logic.